Okay, now weak acids have a different way of being calculated in terms of their pH. Now the formula you use is still based on the Ka expression, which is just the expression to do with equilibrium. Now if we look at the equilibrium expression for a general acid HA, it dissociates into H3O plus A minus, which of course is the conjugate base here. Now to give you an example, it would be the same as ammonium, which is a weak acid, which dissociates into the hydronium ions and NH3, the conjugate base. So the general expression is Ka equals H3O plus times by A minus over HA. Now, because when this dissociates, you are probably going to get roughly equal amounts of this. So if you had 0.1 mole of this, you would have 0.1 mole of that. We can consider these two to be approximately equal. So that changes to being Ka equals H3O plus squared over HA. Now, this is making a couple of assumptions here. And when you do calculations, those two assumptions are: one, that these concentrations are equal, which isn't quite true because there's already going to be a little bit of H3O plus present in the water. And the second assumption is, in these calculations, we assume that the concentration of HA doesn't change much. So in the problem, if it says 0.1 mole of ammonium, for instance, which is a weak acid, we're going to use that 0.1 down here as being the concentration of the weak acid. That is not entirely true because some of the ammonium has been converted into the conjugate base here, but it's such a small amount that we consider it to be effectively the same concentration. For instance, an example of a calculation question would be this. You'd be asked to calculate the pH of 0.18 mole per litre ethanoic acid with a Ka of 1.8 times 10 to the negative 5. Now the first thing in these questions is to work out what formula you need. Now you have to identify that this is a weak acid and that you don't use the buffer formula, which you may have not come across yet if you're just listening to this for the first time. And because it's just a weak acid, you're going to use this formula. So it helps if you write down the formula. It's always a good idea, and then you decide what you're going to put in there. Now the Ka value obviously you've been given, and that's just going to go straight into there. If you ask the pH, this is what you're trying to work out here, the concentration of the hydronium ions, and this concentration of the weak acid goes in there. So then that becomes 1.8 times 10 to the negative 5 equals H3O plus squared over HA. Now that then becomes 1.8 times 10 to the negative 5 times by 0.18 equals H3O plus squared, and then you do the actual calculation. Okay, so you do the calculation like this. You bring the concentration of HA, which is 0.18, up to this line to multiply, equals H3O plus squared. Okay, you multiply them, and then that becomes, you take the square root. Remember, this is squared. It's an easy mistake to make, so it becomes 1.8 times 10 to the negative 3 equals H3O plus. And then if you take the negative log of that, you're going to get 2.74. So pH equals 2.74. Okay. Now, at this stage, that's one example of the calculation. Now, this is really a similar question, but just asking for a different value, and you should kind of be used to that, just substituting in different values to get things. Now, this is asking for a concentration of a weak acid. It's got a pH of 3.1 and a Ka of 1.8 times 10 to the negative 5. So if you set up the equation, which again is a good thing, which is H3O plus squared over HA, being asked for the concentration of the weak acid. That's what that is. You've been given the Ka value. And this here, you've been given because you've been told the pH is 3.1. Okay, so you just need to substitute those values in. Okay, so I've just quickly done that. I've calculated this by going, inverse log minus 3.1. When I do that, I get this value here, 7.94 times 10 to the negative 4, and that's got to be squared. Okay, so 7.94 exponent negative 4 squared equals 6.3 times 10 to the negative 7 over HA equals Ka. So if I effectively swap those two around, I'll be able to do the calculation. Okay, so now all I've done is rewritten this to show that we're going to be dividing this value here, which was the concentration of the hydronium ions, which I got from here. It's been squared. I've rearranged it algebraically. It's going to be divided by Ka, and that means that actually equals 0.035. Now always remember units, because they will mark you down for not using them. So that's a second type of weak acid calculation you could get using this formula. The third is a little bit different and is usually more for excellence. Okay, now finally, a kind of question that would be, I'm just going to try and make sure this is centered properly. Okay, that would be considered more excellence. It's asking for a mass. Now whenever you see a question asking for a mass, it is usually asking for a concentration, and you just have to do something at the very last part of the question to convert that concentration into a mass. So yeah, I just need to change one thing in this question, in a volume of say 200 mils. Okay, now so it's asking for the mass of ammonium chloride needed to make a weak acid of pH 5.4 and a volume of 200 mils. Now, you've got to first of all also recognise that ammonium chloride is a salt, and that when you put it into water it's going to split up into ammonium and chloride ions, and that the ammonium ions are a weak acid, so you're going to be using the weak acid formula. Now the concentration of HA is what you're interested in, and H3O plus you're going to get from the pH, which is 5.4. You've been given the Ka value here that's going to go in there, so it's just a matter of substituting in and solving it. Okay, so all I've done here is I've put the Ka value here. I've converted the pH of 5.4 into the hydronium ion concentration down here. It still has to be squared and over HA. Now, if I rearrange this, so I'm going to put the HA here, and I just bring the 5.6 times 10 to the negative 10, I should be able to solve that. Remembering, I still have to square this value here. So, okay, which I've done, and then I divide by 5.6 exponent negative 10. And I get a concentration of HA equals 0.0283 moles per litre. Try and use a reasonable amount of significant figures. 3 is usually what's expected, depending on the question. Now I've got the concentration of the acid, and I just have to multiply by the grams per mole to give me mass. Now that would be how many grams in 1 litre. So I'll just multiply that by 67.45, and that equals 1.9, roughly, just a second, So that equals 1.91 grams. And if you divide that by 5, you'll get 0.38, 2 grams rounding, in 200 mils. So what I did there is I multiplied the concentration by the molar mass which had been given, and that gave me 1.91 grams. That is in 1 litre. Now we wanted 200 mils, so I just divided that by 5 to get the mass in 200 mils. Now you can use the formulas for concentration equals moles over volume, and also moles equals mass over molar mass to calculate it directly with the 200 ml volume being put in there, etc. But I found this intuitively, I find this way just as easy, so it's really up to you what you want to do. And so that's the majority of all the different types of equations you can have for weak acid. And what you'll find is they're really the same for weak base, but a little bit different, and even some of the buffer calculations are very similar as well.